Gentlemen, thank you for joining us today for this webinar titled How to Directly Print Molds for Composites in Less than a Week, brought to you by Composites World and presented by Massivit. My name is Jeff Sloan. I am Editor-in-Chief of Composites World. Today's presentation will last about 45 minutes, followed by question and answer. If you have a question, you can type it at any time during the webinar under the question tab of your webinar control panel. This webinar is being recorded and when complete will be made available to you via email from Composites World. Today's presentation has three parts. In the first part, I will provide a short overview of additive manufacturing with composite materials and how it has been used to manufacture composite molds. Then we'll hear from Michael Clark, Composites Manager North America for Massivit, with our main presentation. And then finally, Nir Dvir, Industrial Solutions Manager at Massivit, will provide a live demonstration of Massivit's printing technology. So I will get started with a short introduction here. Bear with me. So again, a quick technology introduction here for you. We'll be discussing 3D printing of molds and tools with fiber reinforced materials. So the manufacture of molds for composites manufacturing and fabricators falls into three broad categories, and you can see them listed here. They range from steel, the metallic steel, invar and aluminum, through composite materials themselves, and then into tooling board. Each has its own attributes and challenges. Steel and invar and aluminum are generally favored for their durability and for their ability to withstand the thermal cycling of an autoclave process. They tend to be higher quality. They tend to be fully isotropic, but they also tend to be relatively high cost and have long lead times for fabrication. In the middle are the composite materials themselves. Quality tends to be not quite as high, but the build speed is faster, and they are autoclave capable. CTE tends to be tunable, and they can be used in a low rate or a full rate manufacturing environment. And then the third material is a polyurethane tooling board. Tends to be used in a prototyping environment, can be autoclave capable partially, but the benefits here are relatively low cost and very fast build. So this material is easily machinable and can be used to test designs in a prototyping environment, and that's generally where they're favored. So I want to talk briefly now about additive manufacturing. Additive manufacturing in the last 10 years in the composites industry has evolved very rapidly. And in this environment, we're talking about use of printable materials with fiber reinforcement. And these manufacturing technologies have a variety of scales and formats and materials that they use. They range from desktop units like the kind made by Mark Forged to gantry and robotic systems. All of these have continuous and discontinuous fiber reinforcements. Discontinuous fiber reinforcement has been dominant, although continuous systems are ascendant, and we're seeing a lot of activity here, and this is a very dynamic manufacturing environment. Resins tend to be thermoplastics, with ABS being used the most. There are, however, thermoset additive manufacturing systems available today. Continuous composites, shown in that lower right-hand photo, would be a good example of that. Overall, FDM is the primary technology used for fabricating anything using fiber reinforcement, and applications range from discrete parts to mold making, and we're going to talk about mold making here quickly. So, when you're making molds using additive manufacturing, we're talking about layering a thermoplastic material, usually through an extrusion head, onto a printable surface. And it's typically built horizontally, but as you can see with that mTORUS system, you can also print vertically. The The advantages of this system are pretty significant. It's relatively high speed. It's a low cost system, and the molds that are produced from this additive manufacturing process can be thermally cycled in an autoclave or an oven. Certainly not to the extent that you can with an Invar or steel mold, but the cost and the speed strengths, the cost and the speed are significant advantages in this environment. There are some challenges as well. The primary one is that the materials are anisotropic, and there's just no way to get around that. And because of that, there are significant CTE challenges. And so using this material in a mold making environment means managing CTE and understanding what the CTE is and designing to accommodate that CTE so that parts that come off these molds meet the dimensional requirements. The other challenge is there's generally poor Z direction strength, and Z direction refers to that layer to layer strength. Because you're building these molds with beads that are laid down one on top of the other, that adhesion or that strength between layers tends to be less than it is in other directions. And so managing that strength and dealing with that is a significant challenge of this process. In spite of all this, this is an appealing technology for mold building. But again, there are some limitations here involving anisotropy and Z direction strength. But it's a very dynamic environment, and we're seeing a lot of activity here. And so that brings me to the end of this quick overview of mold building for composites and the use of 3D printing and additive manufacturing in the mold making environment. And so now I'm going to turn it over to Michael Clark with Massivit, who's going to take us into the primary presentation of today's Massivit webinar. Michael, off to you.
Good morning, everybody, depending on where you are in the world. I'm going to try to share my screen here for my presentation. Let's see how this happens. Okay, can everybody see my screen? Or let me know if you can't. Anyways, so my name is Mike Clark, and I've been with Massivit for about a year now. I've been in the 3D printing industry for 4.5 years, and before that I was in the composite industry for over 15 years, selling equipment and materials at different stages. So we're going to get right into it. We're going to talk a little bit about Massivit, and then specifically this new technology that we call cast in motion, which actually combines two of our technologies. So as we move along, I do have to, what's going on with my presentation here? There we go. We do have to put this out. We're a publicly traded company as of last year, so we need to talk about the safe harbor. Okay, so we're going to transform manufacturing of large parts. So when Massivit first started, they came up with a new disruptive technology called gel dispense printing. And what that is a UV cure gel that cures immediately while they're printing. And this enabled us to go up to 30 times faster than any other technology to build prototype parts. Now we build on that technology to develop the cast in motion, and I'll get into that in just a moment. But Massivit is the largest and fastest enclosed 3D printer in the world. A lot of the examples that Jeff was showing were these big gantry style 3D printers that don't necessarily control their environment, and that's what we do with our printing process and our build chamber. Is it's a controlled environment. So Massivit has been around since 2013, and we've been out of stealth mode since 2015. We've sold about 150 to 160 machines worldwide in about 40 different countries. And on this slide, you'll see all the different industries that we're currently in. Some of the heavy industries like rail, aerospace, automotive, marine, we've sold all our systems into. So the cast in motion technology is going to overcome bottlenecks in creating the mold for composite manufacturing. So we're going to do a little poll right now and ask, how long does it currently take you to build a composite mold? Now, if you're using other techniques like CNC machining, please add that in there also, including the queue time to produce the mold. I do not see results coming in just yet. Polls. So I do not see the results. I don't know what I'm doing wrong here. All right, let's move along. And when I get the results to the poll, we will address it at the time that they come in. We got a little bit of a technical issue here. Okay, so as we move along, so we got um, composite manufacturing of molds. So typically, when that happens, here's an example of what we call the modern technology of mold building now, which is basically subtractive manufacturing or CNCing of the master tool, the plug. You can see that in the center, and you can also see some manufacturing in the photo on the right. And on the left, you can see some of the storage challenges you have with building an expensive mold that you don't necessarily want to disregard when the project is over in case the project comes back. With digital manufacturing and 3D printing, that dynamic can change also. So the conventional mold production workflow is you take a CAD file, you produce the mold, and then you can produce the part. And typically, and this is why we asked the first poll question, typically it's 5 to 8 weeks to produce the mold. And we're going to try to condense that. But now we're going to have another poll question, and let's see if the technology is working. I don't know if you guys can see the poll, but it's, how do you manufacture molds today? Hand layup, CNC machining, additive manufacturing. I don't manufacture molds. As we get through the presentation and we talk about some of the time cycles, Massivit is focused on a conventional laminated composite mold. So when we talk about 8, 10, 12 weeks, sometimes longer, it's a very labor intensive process to build a mold. But if you're CNCing something out of a billet of aluminum, it may be quicker. Okay, here. I do get some results to the polls. How long does it currently take you to build a mold? Less than 2 weeks, about 18%, 2 to 4 weeks, 22%, 5 to 8 weeks, 30%, and more than 8 weeks, 30%. I'm rounding up a little bit there. So that is kind of in line with what we've seen in the industry. And if it's less than 2 weeks, typically it's either a very small mold that you can make from an existing part. So you're not even making the master tool. You're maybe splashing it off of an existing part, or you're CNCing something that you don't have a large queue in your CNC department. The next poll question was, how do you manufacture molds today? And just about 30% said hand layup. Another 44% said CNC machining. Now that can either be out of a billet of aluminum or some type of high density foam. Additive manufacturing 9%, and I don't manufacture molds is a whopping 17%. So as we move on, um, there we go. We look at the mold building process conventionally with a hand layup as about 19 steps. Some of my colleagues have mentioned that it may be much more than 19 steps. So we're kind of generalizing. And an example there is um, the final step, number 19, prepare the mold surface. Once you remove the mold from the master tool plug, you typically go through another 4 or 5 sanding steps, all the way through wet sanding, and then a couple polishing steps, a couple buffing steps. And then you have to seal the mold with a mold sealer before you apply the semi-permanent mold release. So I think I just mentioned another 8 or 9 steps. But for simplicity's purposes, there are 19 general steps to make a mold after you have the CAD design. So what we're going to attempt to do with our 3D process is go from the CAD design to 3D printing. You have a mold, now you can make an end-use part. So instead of 19 steps, imagine if it was only 4 steps, which is basically we got the CAD design and then we can print it, which is virtually operator free. And after the printing, we have to post cure it. And I'll explain all these steps in more detail as we move on. And then we have to soak what we just printed to remove the shell layer. And the mold comes out with a fairly rough surface. I can't put a number on it, but it's probably the texture of the thread on a screw if you ran your thumbnail on that. So it's not mold quality coming right off the printer. There is some finishing. The mold material, which is a 2-part epoxy, um, is workable. It's sandable. It doesn't tear up sandpaper. It doesn't junk up sandpaper. So you can hand sand it and then buff and polish it. You can hand sand it to get down the rough edges, the high spots. And then we are developing a coating process where you can spray coat something similar to automotive paint. It lays down like a paint. It air dries, and you can achieve with the painting and very little buffing and polishing a Class A mold finish. So imagine going from 19 steps down to 4 steps. The printing typically, depending on the size of the part, takes 1 or 2 days. The post curing takes about 10 hours. The soaking takes about 24 hours in a tank of water. There's no chemistry, there's no heat, there's no agitation. It just has to soak. The material that we've developed, it is a hybrid of our gel dispensing printing, a GDP, is a water breakable material. So when it sits in the water, it just starts falling apart. We'll have a couple videos to show that. But what this basically does is eliminate the labor needed to build a mold. So 4 steps instead of 19 steps greatly reduces the time and also greatly reduces the labor. So we want to talk about a little bit about how we do this now. We're going to get into the nuts and bolts. So we have 2 print heads in our printer, 2 completely different technologies. The print head you see on the left is the gel dispensing technology. So that is printing a gel-like material. It's about the consistency of toothpaste, and it is surrounded by UV lights, and it cures instantly. And because it cures instantly, it does not need supports. So we have examples where you can literally print a horizontal surface by printing next to the previous layer, side by side, and it's instantly being bonded to its neighbor. The print head on the right is part of a mixed meter dispense system where we are dispensing a casting epoxy. It's a thermoset 3D printing process. So basically, let me go to the next slide. We are printing about 7 to 10 layers of the sacrificial shell material. And then that print head moves out of the way and we pour the casting material in that gap. So we're printing an inner and outer layer of the sacrificial shell, and it creates a gap. It's about 20 millimeters wide. And in that gap, we pour the thermoset material. Now, we do this for two reasons, the reason we're staging it. And the primary reason is when a thermoset material cures or cross-links, it creates heat. It's exotherms. And if you have a large mass, that exotherm really runs away from you and gets quite hot. So by printing 7 to 10 layers and then pour printing, and then printing another 7 to 10 layers and then filling the gap with the epoxy, we're doing two things. One, we're controlling the exotherm. The open time on the epoxy when it's mixed is about 20 minutes. And the other thing we're accomplishing is all those pour intervals, they're blending together because of the open time. And as they blend together, they create a isotropic, rock solid mold. So you don't have any delam issues, you don't have any air pocket issues, and in the X, Y, and Z, you have the same coefficient of thermal expansion. So here you can see it in a little closer detail, although the left photo is of the cast in motion, CIM 155. So that is the dual component thermoset material, and the delivery system is all part of our system, our printer. So we have an auxiliary unit outside the printer that is doing the mixed meter and dispensing of the thermoset material. And the right photo is showing you the Dim Gel 50 water breakable material. That's the UV cure material that is creating the shell. This process is what differentiates Massivit from any other AM technology. So we're literally casting apart with a 3D printer. It's never been done before. And we like the use of the thermoset materials because they have great chemical resistance. The process creates true isotropy, and we're able to better control the CTE, or the coefficient of thermal expansion. So now we're going to run a video of exactly what this process does so you can see it.
The Massivit 10,000 automates tooling for composite manufacturing. This cutting-edge additive manufacturing system enables direct casting with high-performance materials to dramatically speed up tooling. Introducing the world's first isotropic 3D printed mold. The Massivit 10,000 empowers composite material manufacturers to produce custom molds, tools, mandrels, plugs, jigs, and fixtures within a matter of days instead of weeks. The Massivit 10,000 shortens your mold production workflow from 19 steps down to 4 simple steps and eliminates the need for a plug. So how does it work? The Massivit 10,000 utilizes a dual head system to directly print and cast molds. Based on an initial CAD design, the first head 3D prints an outer sacrificial shell at high speed. The second head intermittently casts a thermoset material into that shell as it builds. The shell is comprised of 2 thin walls made of water-breakable photopolymer material that polymerizes instantly under ultraviolet light. The thermoset material forms a solid, isotropic mold. The mold can then be post-cured in an oven to improve its mechanical properties at elevated temperatures. It is then simply immersed in a bath of plain water, causing the shell to crumble away. The Massivit 10,000 offers near-net shape casting. The mold can be post-finished manually or machined as needed. Your high-temp, high-performance isotropic mold is now ready for use within less than a week. Benefit from advanced casting materials that ensure consistent mechanical and thermal properties across all axes. Discover digital tooling for a wide range of industries including maritime, automotive, rail, defense, aerospace, sporting goods, and bathware. Join the digital revolution with the award-winning Massivit 10,000 additive tooling system, offering automated, high-speed tooling for composite manufacturing.
Yeah, that was pretty good. Okay, a couple things I saw there that I didn't mention, and they obviously articulated it a lot better than I could, is you can see what looks like support material on the outside. Those are stiffening ribs. So when you have a large part that may be somewhat flat or just large in nature, we're putting stiffening ribs in there to help the accuracy of the shell material for the casting process. And in the small mold you saw, there was a couple supports on the flanges, and I'll show you that. It was a bike seat mold. The reason for that support is if you were making just a prototype with our gel dispensing material, you wouldn't need those supports. But because the cast material is going to be inside that shell and it has I believe it's a specific gravity of about 1.4. It's a heavy material. It's a dense material. You need to support some of those vertical surface, those horizontal surfaces that are sticking out, the tabs. But I'll show you that again in the slides, the next slides or two. So let's see. So the key benefits of our technology, which is cast in motion, 3D printing composite molds for production, is reduced time. So we can go from 8 weeks to about 5 or 6 work days. The labor reduction, which seems to be an issue with everybody these days, we can reduce that more than 90%. Making a laminated composite mold is very labor intensive, and 3D printing is not. So the reduced the cost can be up to 75%. That is absolutely amazing. This is a newer technology. We're looking for companies that want to adopt new technologies, and we'll work with them to integrate it into their process. So we got another poll coming up here, and that is, what is the average size of the mold you produce today? Because although, as our name suggests, we're massive and we are the largest enclosed 3D printer in the world of composites, things get really big really fast, because the benefit of composites is to save weight, and you want to save weight on large parts. I mean, there are other benefits. Corrosion is a big one, but let's look at the results of the poll and see what we got here. Poll. Okay, so currently 0 to 20 inches, just about 5%. That's really small molds. From 20 inches up to 60 inches is 31% of the 32% of the respondents. 61 inches to 120 inches, 29%. Upwards to 400 inches is 17%, and larger than 400-inch mold, it's a big mold, is 15%. So you can see between the 20 to 60 inch and the 60 to 120 inch, that takes up about 60% of the respondents. Now, one of the things we're working on with this new technology is the ability to print two molds, one at a time at full capacity of the machine and then of the printer, and then bond them together. So let me give you some examples of some of the parts we've made so far. There's a race car seat on the left. The one in the middle that I'll go through a little more later is a sailing wing or a fin for a catamaran, and the one on the right is a radome for a UAV. So a lot of the applications for this technology are to make molds, for composite manufacturing. But you can also make the plug and then make the mold. Or you could just make a mandrels with our wash away material, or just print something that's a prototype. So let's talk about molds, because that's the number one reason for the cast in motion material. So in this slide, what you see is the race car seat mold on the left as printed. It has the shell material on it. And I think you want to notice that we were able to print the support legs. Those aren't necessarily needed to be printed. You could save some time by not printing them. We printed them to show you what you can do. Lights out, very little labor. You can also print the legs for the mold, so then when it's sitting on a table, it's at the right height for the operator. The center photo is showing you the mold. Unfortunately, you're not seeing the mold surface on the back side, but you're seeing the mold with the shell material removed. And on the right, you're seeing an actual part made from that. So now this actual part that we made in our lab, it took 42 hours to print. It's a fairly large part, almost a meter tall, and weighed 53 kilos when printed. That includes the shell material also. So the mold, if I was to guess, would be closer to about 40 to 45 kilos once you remove the shell material. The next part here is the wing for the hydrofoil for the catamaran. Is a mold, is what you see on the left, and the actual part in operation on the right. This part, although large as the race car seat, didn't have the same bulk of the race car seat. So this mold, as printed, took a little over 8 hours and only weighed 16.5 kilograms. Again, that's the complete weight of the mold and the shell material. And here's a little clearer example of the radome part for the UAV. If you look closely at the photo on the left, you can also see that you can produce the mold with some of the trim lines needed for some of the cutouts. So you can print the mold, you got to finish the mold, but you can have those trim lines printed in there. You'll lose some of it in the finishing process, but they can still be embedded in there so that you can use that as a trim process, a trim guide. This part took about 11 hours to print, weighs about 17.75 kilograms, and you can see the size right there. And the ribs on the side are to help the mold stand up. They're also strengthening ribs for the mold. Okay, now we're going to talk about taking a tool. A mold is a tool, and how we can combine some features to that mold for the manufacturing process. And you might have seen that in the video. So here we have the bike seat mold to make a carbon fiber bike seat. But what you might not have noticed is the tabs that we've included on the mold. Those are fixturing tabs for when you CNC the mold surface. And In the process of printing, we were also able to print around these inserts that you see on the left of the three mold views. Those inserts are placed on the table, and we print around them, and then we pour, and they become an integral part of the mold, and they're now considered your datum for machining. So as you're setting this up to machining, now you have a machine surface, these PEM type inserts to touch off of for your datum point, for your machining to make it more accurate. Another great example of our water breakable material is to make mandrels. So if you have a mandrel that has a complex shape or different shape where you can't remove the mandrel and you need something like a collapsible core or a washout core, our material is ideal for that also. So imagine you're 3D printing the core material. This is the water breakable material. And then you wrap it with your composite, whether it's carbon fiber in this case or some other type of engineering material. And then, let's see, soak it, in this case, in a nice glass fish tank. Here's a close-up view of what's happening with the water breakable material. And it's important to note that we call it water breakable and not water soluble. The reason is the water is attacking the material and making it soft so that it breaks away, but it does not dissolve into the water. That's important because you can take this tank and you can screen this broken material out, dry it, and dispose of it like any other inert object. It's not toxic, and you can continue to use the water. The water, because there's no chemistry, you're not weakening the solution is not weakening in any way. You can just continue to use the same water. So another application, and it doesn't speak directly to the cast in motion technology and the Massivit 10,000, but our gel dispensing technology allows us to make custom marine parts, plugs, and prototypes really quickly. And we have some history with that with some of our customers. This, I believe, was a new layout to a bathroom on a boat, and they were able to print this and then back it up with fiberglass and gel coat and install it in the boat. And also do some prototyping and toolless manufacturing. So in the upper left-hand corner photo, what you can see is the swim platform on the back of a boat. The customer was unhappy with the fact that whenever they sat in the salon near the swim platform, and somebody was swimming, they would get splashed a lot. So what we were able to do, or the customer was able to do with our machine, was print these extensions on the side of the boat to help shield the splash from the salon. Another application is on some mass transit, some trains where they're legacy, they're older vehicles, and the parts are difficult to produce. We can scan that, print that, and we have a fire retardant material that we back that up with the proper fiberglass. That can be an end use part. Full scale aftermarket automotive parts, as well as thermoforming molds. If you have a thermoforming project that is 10, 20, 30 parts, you can 3D print it with our gel dispensing technology, back it up with some foam or some fiberglass, and now you have a vacuum form tool in a matter of hours or days as opposed to weeks. And this will show you some of the industries we're in right now with both technologies: aerospace, marine, automotive, defense, infrastructure, and construction. We can talk a lot more about the applications in each of those as the opportunities come up. So what we're going to do now is we're going to run a live demo with Anir from our headquarters in Tel Aviv. So I'm going to need to, I believe, stop sharing. No? Nir, can you hear me?
I can hear you loud and clearly.
Okay.
I hope you can hear me.
Yep, you got the ball.
Okay, so very good morning to everyone. It's a good evening here in Israel, close to Tel Aviv. Mike, I think that you explained so much clearly, and with the video, the only thing I have left to show that it's real and everything in life. We will try to demonstrate everything that Mike just explained. You know what? Maybe we will start first with the machine. Okay, Shai, why don't we take the camera and see the printing process? And after the printing process, I will go deeper into the technology and how we do it. So first of all, the printing process. As we explained, we have two printing heads. What you see here is the printing head, the dispenser, the dispense water breakable material. This water breakable material is casting the shell. I'm casting the shell, and into this shell, I'm going to cast into the shell. I'm printing the shell, and into the shell, I'm going to cast the epoxy material. Okay, so what we see here is a live demonstration of the printing. And if you see the purple light is the UV light that cures the printing. I think we have another cycle to go before we will do the casting. We call the process cast in motion, as we cast as we print. Okay. First of all, we will print a few layers, and then we will cast the epoxy. The reason we do it has to do with the exothermic behavior of the epoxy. It is, of course, impossible to cast a huge amount of epoxy in order to be able to control the temperature of the geometry, the temperature in the printing area. So we will make everything very measured, create the amount of layers, depends on the resolution, and from that point, we will cast the material. So I will let it print another round, and then we will see the casting process. In this demonstration, I will present not only molds, I will present also mandrels, and I will present also printing end parts that can be printed with the Massivit 10,000. Yeah, okay. It's good. Okay. So in about 10 seconds, we're going to see the casting process that will happen. Now, please pay attention, because we cast a lot of material, a lot of epoxy at the same time, just to save time and to cast as much material as possible. Oh, thank you very much. We managed to get to see the casting very well. And the casting head will move aside, and the printing process will continue. And from here, I'll try to show you how we do it. What is the secret behind the speed, the size, and the technology? Massivit 3D has more than 160 units around the world. Most of them are printing with the GDP technology. The GDP technology allows us to print rapidly, one layer on top of each other, and as you understand, cure it immediately. The fact that we can print one layer on top of each other with immediate curing allows us actually to print hollow objects. It means that this geometry was not printed that way, in that orientation, but was printed in that orientation. It means that here it is hollow. When it is hollow, I'm saving time on cleaning, I'm saving on material, and I'm saving a lot of money. This is the GDP technology. Talking about the printing head, this is our dispenser. Actually, a screw inside this printing head is turning and pushing material through a tip. We have different tips to determine the different resolutions. So you have also flexibility in terms of resolution, and this can be easily replaced and used for a different resolution. The gel will dispense out of this tip, and a UV ring, will cure it immediately. If you take a closer look, you will see two rings. This is in order to get the right intention, the right energy to cure more or less, or just to cure the right amount of gel at a spot. Based on that, the Massivit 10,000 will use the GDP technology that we just saw now, and will cast material into it. So what you can see here, this is a product that is coming out of the Massivit 10,000. You can see the shell, and you can see the casted material, the epoxy that was casted automatically with the casting motion technology. So it was printed in that orientation, printed and casted till I have the final geometry. So print, then cure in an oven, then after the final curing, the post-curing process, soak in water. When I will soak it in water, the shell will crumble off, and I will remain, as you can see, only with the epoxy material. With some finishing, hand sand or CNC, you will get to the right surface quality that you want to get. At the end, you all want to create parts out of carbon material. Just a few minutes before we started the webinar, I asked to bring a bigger part, because we show in the presentation a bigger part. This is a motorbike gas tank hood, okay? Made out of carbon material and made in this mold. Shai, I hope that we can see the mold. The mold is already it's a 10th cycle. Here, as you can see, it is under vacuum. Okay, so here we have a mold under vacuum, and we are going to gain additional part out of this mold. Very nice to see that we are not only, Shai, if you can go down a little bit, so we can see the bottom part of the mold. Oh yeah, perfect, thank you very much. So again, you can see that this mold is under vacuum, This is the part to connect to the vacuum, and you can also see the tooling that is part of the mold. Okay, and this has to do. This geometry is in freedom of the creator. If you need better airstream, or if you need holder for your CNC, you can just design them and print them. This mold was printed in less than 24 hours. To be more accurate, it is about 19 hours. And of course, there is a process that is coming after that. So we say molds in days instead of weeks. That's the magic. But it is not everything. Molds, jigs, and fixtures, and also the capability, the ability to create mandrels, okay, molds that are one-timer. I'll come a little bit closer to show it. If you have a shape with the undercut, okay, such as this pipe, for sure you will need a mold, a two-part mold, or maybe more. And in order to get it at the same day, you have the capabilities with the Massivit 10,000 to print a mandrel, water soluble, okay, actually water breakable. I will print it only with the shell material. And with the shell material, I will print it. I will cover it with carbon fiber, cure it, and soak it in water, and I will get my part within hours. Okay, so this is more than you can create with the Massivit 10,000. Another sample that maybe could be nice to show is a sandwich construction here that was done with a GDP printing and coated with carbon fiber. This is the hull of a small jet ski that was done here according to a design that we became. You can see on my side the CMS in the background. The CMS is part of the Massivit 10,000. This is where part A and part B from the epoxy are getting ready, getting heated and prepared to be sent to the machine with pipes. They are going to the Massivit 10,000 and will be mixed with a static mixer at the machine. So practically, after the printing, you can, if you want, you can wash it or just drop it to the garbage and use another one. Very, very simple. Something that we take from the market. I think, Mike, if you think that I forgot something.
No, that was great, Nir. I think the demonstration, the visual helps a lot in introducing this technology to our attendees. I thank you much. I know we want to get to a question and answer. I don't see that in the platform if we have many questions, but I did want to offer to everybody. Let's get back to maybe my screen so we can start addressing any questions. You guys just go into the chat function on the platform, and Nir and I will try to answer them as quickly as possible.
Okay, thank you, Mike, and thank you, Nir, for that presentation. Really interesting technology. So we do have a few minutes. Well, we have about 5 minutes for questions. So attendees, if you do have a question, go ahead and put it into the Q&A tab. Mike and Nir, we have a lot of questions already, so I'm going to just get right into these. Some of these questions fall into the same category, so I'm going to aggregate some of these questions, but a lot of them revolve around material properties. So I'm going to start with a couple basics. What is the CTE of the epoxy and what is the TG of the epoxy?
Okay.
Um,
Go ahead, Nir.
okay, in terms of CTE that we are promoting now, we talk about a CTE of 31 ppm, and targeting in the next months to come to CTE that is lower than aluminum, means lower than 23. In terms of temperature capabilities, if we talk about TG, we talk about 150 degrees Celsius. Okay.
So that the T sub G, or the glass transition temperature, is 155, but the
Yeah.
heat deflection temperature is 150. So that's really the
Yeah.
workable temperature, is 150 C. Into Nir's point about the CTE, it's comparable to aluminum right now, and we're working. That's kind of our secret sauce. We're working on improving that, in elevating the temperature. So our goal is to have materials that are autoclave safe, which is typically 180 C, and to have a CTE closer to some of the um, tooling epoxies, or something like Invar in the single digits. That's on our material roadmap.
Okay. And what about thermocycling in an autoclave? How compatible is the epoxy with that?
Unknown. It's a new technology. We're introducing it in the market right now. We have 2 beta customers. One is up and running and live right now in Israel. The second one is going to be in the United States and should be up and running in the next couple of weeks. The material is not compatible for full autoclave. And what I mean by that is that 180 C, we're not there yet. If you need to post cure a part on the mold, and you're in the 350F, which is about 140 C, do that all day long. As far as the durability, we don't know. I can tell you we can hit this stuff with a hammer. It's strong. It's solid. It's not a laminate, so you're not going to get the degradation in the heat cycling that a laminated mold gets. But we can't predict the future.
Okay. 2 other questions. Is it possible to add fiber reinforcement to the epoxy? Have you considered that? Also, how do you minimize voids and air bubbles in the epoxy as it's cast?
Okay. Part of our material roadmap is to add fiber to increase the mechanical properties. We're not there yet. They're in R&D. What was the second part of the question?
Air bubbles or voids in the
Oh,
cast material?
that's probably our biggest challenge right now. The system that Nir was showing on his left, our right, the CMS, um, both of the materials are under vacuum, so they're completely degassed, and they remain in the vacuum up until the static mixer. So we've worked really hard to remove any entrapped air in the material, but the process of mixing it reintroduces some. So there's a little bit of a challenge there, but the sample parts that we've gotten out, you can see the surfaces don't have a lot of air voids. And when machining, we're not finding new air voids below the surface. So we're addressing it. It is an issue on some of the larger parts. And we're just moving forward from there in the development process.
I can add maybe on top of that today our molds are about 20 millimeter thick, and with that we find no limitation. We do not see any vacuum problem. So our mold holds vacuum, and this mold, as you saw here, is holding vacuum very good, and all the bubble issues are permanently improved.
Okay.
That's a good point, Nir. One of the challenges to a laminated mold is making sure that it is vacuum tight. Sometimes you have to check that and then go back and try to find those those leaks. Because this is a solid and not a laminate, it's naturally vacuum tight or vacuum compatible.
Okay, I'm going to throw a couple more questions at you, and then we're past top of the hour, so we'll wrap up here. Do you have any sense for what the life of a mold may be at 120 C? So how many pulls might be expected at 120 C?
Again, because it's a new technology, we don't have that. If you're asking me to guess, I've been accused of being optimistic before, but I think hundreds, if not thousands. And the reason I say that is I've been in the industry for a long time, and I've seen the challenges to traditional composite laminated molds, and what an air pocket just below the surface, or even 2 or 3 laminates below the surface, can do to the gel coat. And that's just does not exist here. So being cautiously optimistic, I would say hundreds.
If just to add, maybe to answer another question, if the mold is damaged due to any reason, and we know that they are damaged by operating them, they are easily repaired. Okay, so this is also a very, very important point, that the molds are easily repaired.
Excellent.
Refurbished.
All right.
Okay, final question. Can you say anything about the tensile strength of the epoxy or its hardness, bark-hole hardness?
Not off the top of my head. We have them both in the tech data sheet, and we're working on some coatings that are like gel coat, and I do know that the bark-hole on that material is a 92D, which is slightly harder than traditional gel coat, so it's going to have a hard tooling surface.
Okay. Well, Nir and Michael, we are, as I said, we're past top of the hour. We have a lot of questions we weren't able to get to, so I want to assure our attendees that those questions will be saved and forwarded to Massivit for response. So expect that you will hear from Massivit directly to those. So Michael and Nir, thank you again for this presentation. Nir, thanks for having the courage to present this live, and appreciate everybody's involvement, and thank you for the webinar today.
Thank you very much.
Thanks. Take care. Thank you, everybody.
And thanks to our attendees as well for taking the time to join us today. We appreciate you being here, and we hope to see you again soon at the next Composites World webinar. For more information, please visit compositesworld.com. Thanks, everybody, and have a good day.